Welcome back to the video series on integration and differential equations. Today we're going to continue our discussion of homogeneous DEs with constant coefficients. So let's start with this example here, and let's remember that this capital D notation is just alternative notation for the derivative. So when you see capital D cubed y, that's the same thing as saying y triple prime. And on the right side, we've got 9y prime. Okay, so y triple prime equals 9y prime. This is not the standard way of writing these DEs with constant coefficients. The standard way would be to write all the y terms on the left side of the DE, and then if there were any x terms or constants, they would go over on the right side. In this case, our right side is just 0. So all y terms and only y terms on the left side, everything else should go over to the right. All right, so now that that's in standard form, we can say, yes, it is a homogeneous DE, because we do have 0 on the right side, and it does have constant coefficients. In looking at the left side, our coefficients are 1 and -9. We're not seeing any x's or y's in those coefficients, so that looks great. Okay, so that tells us that we can set up our auxiliary equation. Y triple prime becomes an m cubed, and the y prime becomes an m. So here's our auxiliary equation, and we can either factor this or use the quadratic formula. Well, notice especially when there's a higher power of m in the formula, or in the equation, often it's a matter of looking at your two terms and seeing if there's any common factors that can be pulled out. So in this case, we could pull common factor m out of those two terms, and that way we could factor the left side of the equation as m times m squared minus 9. Okay, so that's equal to 0. And what we would like to do is get this fully factored. So now this m squared minus 9, that's a difference of squares, and that will factor as m minus 3 times m plus 3. So we've now got our left side fully factored, and we can write down all the different solutions to our equation. So from the factor m, one possibility would be that m equals 0. From this factor here, if m minus 3 is equal to 0, then that means m is equal to plus 3. And from this factor here, if m plus 3 is equal to 0, then m would be -3. So we've got 3 different roots here to our auxiliary equation. So I would make a point of saying that we've got distinct real roots. Distinct meaning there's no repeats here when we list the different roots. Real roots meaning we're not seeing any complex solutions at this point. Okay, so we can write down our general solution. We talked in the previous video about the form of this general solution. Each term is going to look like some unknown constant times an exponential, and in the exponent you're seeing one of the m values times x. So our first term would look like c1 e to the 0x, and then we would add on our second term, c2 e to the 3x, and then plus c3 e to the minus 3x. So each of these terms here should have a different unknown coefficient. We've used c1, c2, and c3. Okay, so that's fine, but maybe we'd like to simplify this a little bit. That first exponential is e to the 0, so that just becomes 1. And we could simplify that first term then and just call it c1. c1 plus c2 e to the 3x plus c3 e to the minus 3x. One question that often comes up is sometimes people wonder about the order of the terms, and the idea here is that you can write these terms in any order that you like. So just to give you an idea of some alternative answers, you could have written, say, c1 e to the 3x plus c2 e to the minus 3x plus c3, many other possibilities for orders of terms as well. So just make sure that whatever order you're putting the roots in here, that you're using these unknown constants, c1, c2, c3, but which c1 or which constant gets matched with which term here, there's no strong convention for the order. Here's our last example for this topic. And first thing I want to do here is just to emphasize the notation. So when we see d squared y by dx squared, that's just another way of writing y double prime. So we could rewrite this dE here as y double prime plus 8y prime minus 3y equals 0. Okay, this is written in the standard form because we've got all the y terms over on the left side, and if there were any non-y terms like an x term or a constant, those would be over on the right side. Okay, so this is a homogeneous dE because we're seeing a 0 on the right side. We've got constant coefficients. As we look over at our left side, our coefficients are 1, 8, and negative 3. So that tells us that it's valid to set up an auxiliary equation for this problem. The auxiliary equation is going to look like m squared plus 8m minus 3 equals 0. So we can either solve this equation by factoring or by using the quadratic formula. And it's essential at this point that we know our quadratic formula really well. So I'm going to write it in big letters here. If we wanted to solve this equation using the quadratic formula, we would say m equals negative b plus or minus square root b squared minus 4ac all over 2a. So let's plug in here. Negative b is going to be negative 8, and then we'll go plus or minus a certain square root. B squared minus 4ac is going to give us 64 minus negative 12, or in other words 76, and that's all over double our leading coefficient, so that's all over 2. Okay, now sometimes it's possible to simplify these m values, so let's take a close look at the square root here, and let's think about whether there are any perfect squares that divide into 76. So I'm actually going to cross off just this root here, and let's see if we can rewrite it. So 4 divides perfectly into 76. 76 is 4 times 19. So we could rewrite that root 76 as root 4 times root 19, and then taking that a little bit further, that root 4 is the same thing as 2. So we're actually able to rewrite that root 76 as 2 root 19. Okay, and the reason why that's great is because then we can take this numerator on top and we can divide everything through by 2. So dividing both terms by 2, we get m equals negative 4 plus or minus root 19. So by doing that simplification, we're avoiding fractions in our roots, which is really nice. Okay, so we've now got these two roots. One is negative 4 plus root 19. The other one is negative 4 minus root 19. So these are distinct real roots. Okay, they are distinct roots because there's no repeats here. And they are real roots, so let's take a second and just make sure that we're super clear on this. These are real quantities. The quantities under the square roots are positive. Okay, so these are real numbers. They're not particularly nice, friendly numbers, but they are real numbers. A little bit later on in the video series, we'll talk about how to handle complex numbers, meaning what to do if we've got a negative number coming up under a square root. So if there were a negative number under the root, these would be complex numbers, but we've got positive numbers under the root. So these are nice real numbers. Not particularly friendly real numbers, but real numbers nonetheless. All right, so let's go ahead and write down our general solution. So y is going to have the form c1 e to the m1x plus c2 e to the m2x, where m1 and m2 are these roots, and let's plug in. Y is going to be c1 e to the minus 4 plus root 19, and that's all going to be multiplied by x. So we really do want brackets there in that exponent. And then plus c2 e to the minus 4 minus root 19, and that's all going to be multiplied by x. So there we go. That is our general solution to the DE.